So today's lesson is on the distance and midpoint formulas. So in order to find the distance between 2 points, let's go ahead and assume that we have point P, which is going to be labeled as x1, y1, and then point Q, which is going to be x2, y2. So if we go ahead and plot these, let's go ahead and just plot a random x1, y1, x2, y2. We'll put P over in quadrant 2 and Q in quadrant 1. Our goal is that we end up figuring out the distance. So what is the length? We'll call this D for distance. What is the length between point P and point Q? One way that we could do that is if we go ahead and drop the vertical down and the horizontal across, and make a right triangle out of this, then we can use Pythagorean's theorem. So let's go ahead and label the horizontal side A and the vertical side B. Then what we have then is we would have, if we're doing normal Pythagorean's theorem, we might see something like this, or labeled A, B, and C. That's the normal item that most people remember. So A squared plus B squared equals C squared. So the sum of the squares of the legs equals the square of the hypotenuse. That's Pythagorean's theorem. For our purposes, we're going to label C as D. So we'll just drop that vertical piece in there. And so we see that our distance formula is based off the quadratic formula. Excuse me, not quadratic formula, Pythagorean theorem. Sorry about that. And so let's see, how are we going to figure out A? Well, one of the things that we need to do is we need to figure out, well, what is the coordinate of this point over here? So that coordinate then, and well, how far over right and left is that? Well, that's just the same as x2. Then how far up and down is it? Well, that's the same as y1. So there's that point. Now we can go ahead and we can figure out, okay, what is the length of A here? So the length of A, we're going from x1 to x2. So that's going to be, that length is x2 minus x1. And then it's horizontal, so we don't have to worry about counting any horizontal change. So the y1 to y1 doesn't do anything for us. So A is now x2 minus x1. We can do something similar with B here. B's length, as far as its x components, it doesn't change in the horizontal, so we can just let that stay as is and not worry about it. We're only going vertically, and so that changes whatever the distance is from y2 to y1. So that is going to now be our B. If we take this and go back into Pythagorean's theorem that we did earlier, now we have A squared is x sub 2 minus x sub 1 squared plus B squared, which is y sub 2 minus y sub 1 squared, equals the square of the distance then between those 2 points. Interesting, we were not interested in D squared, we're interested in just in D. So the way to get rid of the square is to go ahead and take the square root, and in an equation, we take the square root of both sides. So what that does for us then is we have the difference in the x's, that quantity squared, plus the difference in the y's, that quantity squared, that whole thing underneath the square root equals D. So that is indeed the distance formula. Normally we rewrite it a little bit and we put D first. So the distance between any 2 points is the change in the horizontal distance squared plus the change in the vertical distance squared. And that is our distance formula. So that is the distance between any 2 points. And that's what we're saying here. The distance between points P1 and P2 denoted by distance between P1 and P2 is this particular formula. So let's go ahead and use that. Let's use that to find the distance between these 2 points, between -4,5 and 3,2. So let's see, our distance, if we write the distance formula down again, is the difference in the x's squared plus the difference in the y's squared, and we square root that whole thing. Let's see, as a matter of notation here, we've got a couple of points. Let me move this down. So this will be x1 and y1, and there's x2 and y2. So just designating one as our first pair of points, x1, y1, and x sub 2, y sub 2 as our second pair of points. So we fill these in. So x2 is 3, x1 was -4. That quantity squared, plus, let's see, y2 is 2, minus y1, which is 5, that quantity squared, and of course we're square rooting again the whole thing. So now our distance equals, let's see, we got 3 minus negative 4. Double negative turns that into a positive, so that becomes 7. So we got 7 squared. 2 minus 5 is negative 3, and we'll square that. So 7 squared is 49. The square of negative 3 means negative 3 multiplied by negative 3, so that's positive 9. We'll come to that in just a moment here. And then square root of 49 plus 9 is square root of 58. And that is our answer as far as what is the distance between those 2 points. And if we plug that into a calculator, we're going to be approximately 7.62, if you want to go ahead and check that out. Now, one thing I do want to come back in and just double check is this term here, the square of negative 3. One item that's a common mistake that students will make on this is that when we take this item, negative and 3 squared, that's not the same as this item, the square of negative 3. Interesting enough, what happens then is on this first one, we have the negative, and then we have 3 times 3, and that's going to end up being negative 9. On the second one, we have negative 3 multiplied by negative 3, because our exponent applies to both of these items, not just one of them. It applies to the negative and to the 3. And on the first one over here, all we applied the square to was just the 3. So negative times negative is going to be positive. 3 times 3 is 9. So negative 9 is not the same as positive 9. And that is one of the things that we do need to be aware of as we take a look at those. So let's use algebra in example 3 here to go ahead and solve a geometry problem. Oftentimes geometry questions will set something up with a shape, and then we solve things with our algebra skills. So let's consider these 3 points. Let's do A, which is negative 2, 1, B, which is 2, 3, and C, which is 3, 1. So 4 things we want to do on this one as an example. We're going to plot each point and form the triangle. Then we'll go ahead and find the length of each side using the distance formula. We'll show that the triangle is a right triangle, and then we'll also find the area of the triangle. So first things first, one of the things we want to do then is we just want to plot this. So let's see, we have our x-axis, have our y-axis, and let's see here. So we're going to go 1, 2, 3 along the positive x, negative 1, negative 2 along the negative x. Looks like everything's positive in terms of y, so it's 1, 2, 3. We'll get it that way. So we've got, negative 2, 1 is going to be here. That's point A. 2, 3 is going to be up in here. That's B. And then C is 3, 1. There. So we'll go A to B, B to C, and from A to C. And if we notice A to C, both the y terms are the same. They're both 1. So we're not changing anything in the vertical component. So the line AC is indeed a horizontal line. Okay? So let's see. Plot each point and form the triangle ABC. That we have accomplished. Let's take a look and find the length of each side of the triangle. So what we want to do then is we want to find the distance from A to B. So let's see. So on this one, we want, and it doesn't matter which point we label x2, y2, x1, y1. It doesn't matter either way. They still end up the same. So for our purposes here, let's go ahead and label A as the first point and B as the second point. So if we take our formula here in general, just to put that back up here, was the difference in the x's squared minus the difference in the y's squared, and square root that whole thing. So x2 minus x1, let's do, let's see, 2 minus negative 2 squared. So we're taking these points here. Okay. And then minus, oops, I'm sorry, that should be a plus sign there. We're adding those. Slight mistake there, slight correction. And then let's add then the difference in the y values. So we got 3 minus 1 squared. As we finish solving this one then, let's see what we end up with. So 2 minus negative 2 is 2 plus 2, so that's 4. 4 squared is 16. And then we've got plus 3 minus 1 is 2, and 2 squared is 4. So when we put those together, we end up with the square root of 20. So that's the distance from A to B. Let's do now the distance. Let's change colors here to coordinate this a little bit. Let's do distance from B to C. Okay. So now we'll end up using these 2 points. So on that one, so we end up difference in the x's. So let's see, 3 minus 2 quantity squared plus difference in the y's. So 1 minus 3 quantity squared. So 3 minus 2 is 1. 1 squared is 1. And then we have, let's see, 1 minus 3 is negative 2. The square of negative 2 is positive 4. And so that ends up being the square root of 5. Now let's take a look at our third piece. Let's do the distance from A to C. And what I'm saying on this one overall is we could just count this. So going from A to C, I've got 1, 2, 3, 4, 5. So I'm contending that this is going to end up being 5. Let's go ahead and use Pythagorean's theorem, though, along with our distance formula. Let's go ahead and figure out what that is. So let's see. If we go ahead and take A and C, so we come back up here. So we're doing A, and we're doing C. So let's see. So x2 minus x1. So let's do 3 minus negative 2, that quantity squared, plus difference in the y's. Well, they're both 1. So that's 1 minus 1 quantity squared. So 3 minus negative 2 is 3 plus 2. So that becomes 5. 5 squared then is 25. 1 minus 1 is 0, and 0 squared is 0, so we end up with 25 plus 0, the square root of that, which really ends up being the square root of 25, and the square root of 25 is indeed 5, which is what we said it was just a moment ago. So it illustrates the idea that when we are taking a look at these components as far as either horizontal or vertical, we could just count. We could count horizontally or we could count vertically, and that would be okay. So let's see, A to C is 5. We say AB is square root 20. So let's go ahead and write this up in here. So that was the square root of 20, and BC we said was square root 5. Okay. So we've accomplished part B as we go ahead and take a look at those. So the other thing we want to do is show the triangle is a right triangle. Well, if we go back to our geometry skills, in geometry, if we have 3 sides forming a triangle, it will be a triangle if Pythagorean's theorem is true. So if a squared plus b squared equals c squared, then we're a right triangle. And if we're a right triangle, that's what we're trying to show here. So let's take our pieces. Let's see, we've got the square root of 20. Let's get right very well there. Here we go. So I have the square root of 20. So we're going to take that and square it. We're going to add to that the square root of 5 squared. And we're checking, is this the same as 5 squared? Because what we're checking here on this one is it appears as though this would be the right angle. Okay. And so is that a right angle or not? Well, if this holds true, then we've got it. So square root of 20 squared, the square cancel, so that's just 20. Square root of 5 squared, the square root and the square cancel, so that's also just 5. And 5 squared is 25. So it's still got my question mark there, although we can readily see here pretty quickly 20 plus 5 is indeed 25. And so 25 equals 25. So yes, triangle ABC is then a right triangle. And we can use some abbreviations in there. So now we know what we have. So we've done parts A, B, and C. We also want to figure out what is the area of this triangle. So if you remember, area of a triangle, is 1/2 the base times the height. Okay? And normally when we do that, the base and the height are perpendicular to each other, which works out really nicely because perpendicular just means where there's a right angle. So we've got a right angle in there, angle B. So the area of this triangle is going to end up being equal to 1/2. Let's see, the base is the square root of 20. And then the height is the square root of 5. And we could have interchanged the base and the height, and that doesn't matter. Remember, multiplication is commutative, so we can reverse those without any issues. So when we put those together, we have 1/2. Let's see, square root of 20 times square root of 5 would be square root of 100. Square root of 100 is 10, and 1/2 of 10 then is 5. So that means then that the area of this triangle is 5 square units. We don't know what the units are, if these are inches or feet or centimeters. All we know is that the area is 5. So we have now accomplished all the examples, or all pieces of that example, example 3, using algebra to solve a geometry problem. There's one other piece that we want to tackle in this particular section as far as the distance and midpoint formula, and that is the midpoint formula. So everything we've done so far had to deal with the distance formula. So we were dealing with this thing. Okay. Now we want to go ahead and talk about, well, midpoint formula. So midpoint, if we think about what that sounds like, midpoint sounds like middle, and that's what we're going to do. We're going to find what is the middle between a set of points. And so if we take a look at this particular example here, we're going to prove the midpoint formula. And as we take a look at this, and we'll see what is going on here. And we say, given that m, so m would be the midpoint, that is xy, so that is this point here. We're going to prove the midpoint formula here. So given that m is the midpoint, and it is the same distance from P1 and P2, so same distance from point 1 down here and point 2 up above. That's thing that one thing we're told. And let's also say then that segment from P1 to A, so P1 to A, this piece down here on the bottom, is parallel to this piece here, MB. And let's also say then that the vertical pieces are parallel from M to A and P2 to B. So if those are all the same, those are parallel, let's see what this proof looks like. Okay. So here's what our item is going to look like. So when we're doing a proof, we start off with some of the things that are in our setup here. So we're going to say, let's take a look at angle A, P1 to M. So A, P1, M, so it's this angle down here in the lower left. So that angle there. And that is going to end up being equal to, it's going to be equal to angle, oops, got some other things popping up here, to angle B, M, P2. So this angle here. And that is going to be true because we were already told that we had some parallel lines in here. And so because we have these parallel lines, because this line here is parallel to that one, so those two angles are corresponding angles. And corresponding angles are always congruent. And congruent means that then they are going to be equal to each other. So I could put the congruent symbol up there to be a little more accurate. So what else do we have? So we have those angles that are congruent. Then we also have, let's see, what else can we come up with? Oh, we've got another set of parallel lines, right? So another set of parallel lines is this line and that line are parallel. That means that this angle here, P1 to M to A, so that angle is going to be the same as M to P2 to B. So those angles are going to match. So let's go ahead and write that down. So we can say then that angle P1 MA is going to be congruent to, let's see, M P2B. And again, because these are corresponding angles, they have to be congruent. So if I erase some of that extra notation here and see, well, what do we have? We've got these angles equal to each other. And then we also have, let's see, this angle and that angle equal to each other. The other things that we have then is we are told that PM, okay, PM is equal to P1 to M is equal to M to P2. Okay? And so that was this piece up here. Given M, which is XY, is the point that is the same distance from P1 to P2. So we can mark these two marks the same. So that was given information to us. Then what we have, if we take a look at these triangles here. So I've got this triangle, I've got this triangle up here. What we have is we have an angle, a side, and an angle. So we have this angle here, that side, and then the angle. Then we have a corresponding angle, the side, and another angle. So what we can say then is that these two triangles are going to be congruent to each other. So we can say that triangle P1MA is congruent to MP2B. So my triangle symbol in there. And that is by the angle side angle congruency. So once we have all that, then we can also come up with some other statements. So the other statement we can come up with then is that corresponding parts of congruent triangles have to be congruent. So that would tell us then that, let me erase some other pieces here, so that this side and this side, since they're in the same relative positions to each other, have to be congruent. So what is the length of that side? So that is, let's see here, that is x minus x1 is going to equal to x minus x2. So x minus x1 is the length of this piece, and x2 minus x is the length of that one. Oops, I reversed those around here. So let's do x2 minus x just to be a little more consistent. Also then, the vertical pieces have to be congruent. So this piece here, whoops, let's change colors again. So this piece here and this piece here have to be the same because they're the same parts of the congruent triangles. So that would then be, let's see, y minus y1 is this first piece, and then that has to equal then y2 minus y, which is that piece. And you see that these were already labeled in here as well, y2 minus y, y minus y1. And on the other side, we also had x minus x1 and x2 minus x. So that is those lengths of those sides, since we're going horizontal and vertical components. And all of that, if we're trying to list reasons, is that corresponding parts of congruent triangles are congruent. Okay? Now, as we get into this, I don't want you to freak out and say, oh my gosh, this is college algebra, that's a lot of material in there. What we do in college algebra is we try to explain why sometimes the formulas work. So this is the setup on why the formula works. In just a few moments, we're going to have the final formula, and then that's the thing that you're going to need to remember. Okay, so you will not have to, in the course of the class, to recreate this proof. All I'm doing is showing you how the formula comes about. So as we take a look at the rest of these things, let's go ahead and move some things around with our algebra skills. So let's see. Let's see. I've got on the orange here with the x's. Let's go ahead and take this minus x and move it to the other side. So I'm going to add an x. So I've got an x already, so now it becomes 2x minus x1 equals x2. And let's see, if I want to get the x's by themselves, just x, not the x1s, x2s, let's move this minus x1 to the other side. We'll do that by addition. So 2x equals now x2 plus x1. And I'm going to go ahead and rewrite that so I have in numerical order x1 plus x2. Again, it really doesn't matter, but just for the sake of some consistency here in a moment. Then to get x by itself, I've got two x's. To get x by itself, I divide by 2. So that means this x coordinate is going to be x1 plus x2 divided by 2. That's what that x is. So really, it's the average of the x's. Take two things, add them together, divide by 2, you're doing the average. We're going to do something very similar here then to the y's. I'm going to move this, let's see, minus y2 minus y1. Hopefully you caught that. That was y2 minus y. Minor mistake there, so we pick that one back up. Let's move those out of the way. So if I want to move this minus y to the other side, I'm going to add that. So like the x's, I have 2y minus y1 equals y2. Then if I move this minus y1 to the other side, I move that over by addition. So then I've got y1 plus y2, and I'm just going to flip-flop those immediately. Then to get the y by itself, we divide by 2. So the y value then is the average of the y's, and that's this value. So if m is indeed the midpoint, which is what we were saying, then that we know that that midpoint, the x coordinate is x1 plus x2 over 2, and the y coordinate is y1 plus y2 over 2. Which leads us then into the actual midpoint formula. So midpoint formula is nothing more than the average of the x's and then the average of the y's. That is the midpoint formula. So out of this whole item here, the thing that we will need to be remembering out of that whole setup is just this last piece. Okay. So let's go ahead and use that. Let's go ahead and use that to go ahead and find the midpoint between two items. Let's find the midpoint between point 1 and point 2. If point 1 is negative 5, 5, and point 2 is 3, 1. So as we take a look at those, I'm going to go ahead and graph those. Let me get some grid lines up here. It lets my graph be a little bit better than what I would normally do just on my own. Let's see, so 1, 2, 3, 4, 5, negative 5, and then 1, 2, 3, 4, 5. So where those intersect, there's point P, and point P1, I should say, and then point P2 is at 3, 1. So 1, 2, 3, 1. So there's point 2. And then we're saying if we go ahead and we take a look at those, where's the midpoint? Okay, so what appears, though, just by guessing, the midpoint is going to be right around in this area. So just by graphically, I'm going to guess that that's going to be negative 1, 3. Okay? And when we have our grid, sometimes we can look at it and come pretty daggone close. But let's go ahead and do the midpoint formula. So the midpoint formula says that we're going to add the two x terms together and divide by 2. We're going to take the two y terms, add those together, divide by 2, because we're taking the average of the x's, the average of the y's, and average gives us the middle of those items. So let's see what we can do here. So let's see, m equals, let's see, we'll let this be our first point, and this one then be our second point. So x1 was negative 5, x2 is 3, divide that by 2. Then y1 was 5, y2 is 1. We'll divide that by 2. So our midpoint, let's see, we end up with negative 5 plus 3 is negative 2 over 2. 5 plus 1 is 6 over 2. So our midpoint then, negative 2 over 2 is negative 1. 6 divided by 2 is 3. So our midpoint then is negative 1, 3, which graphically we could have kind of had an idea about where that was, and it happened to work out. Okay, so that is the end and the conclusion of section 2.1, distance and midpoint formulas. Just to recap just for a moment here, the major items and the distance formula is a twist off Pythagorean's theorem. So that's the difference in the x terms squared plus the difference in the y terms squared. Then the midpoint formula is the x1 plus x2. So adding the x's, dividing by 2, and then adding the y's and dividing by 2. So in one case, we're subtracting and squaring and doing a square root. The other case, we're just adding, dividing by 2. One thing that happens very consistently is that x's will always go with x's and y's will always go with y's. And if we remember that piece throughout the course, some other things then will become much simpler later on. That is the end of this particular section. If you see a mistake, please go ahead and let me know so I can go ahead and fix that. Otherwise, we'll see you in the next section.